And his title is Turbulence and Reduced Order Modeling in the Frequency.
Yep, great. Thanks, Rich. It's nice to be here. I'm a bit jet lagged still, even though I got here yesterday. So if I somewhat incoherent, you'll understand. I also have to apologize. I know many of you actually saw this talk already at APS this year. And, during the pandemic, there have been lots of seminars. So I feel like I've been telling the same story quite a few times. So let's move forward here. So I'm going to show you work from a whole bunch of collaborators, students, postdocs, and collaborators from other institutions. I'll introduce you to the specifics as I get to them. And I also want to acknowledge, of course, funding for a number of years from different sources. So the main topic of my talk is coherent structures and modeling of them. So I don't think I really need to explain to this audience what coherent structures are and why they're important. They are, of course, critical in engineering for predicting and controlling things like drag and aerodynamic sound, mixing, you name it. Another feature of them that's interesting is that they kind of form a connection between what we understand as instability or amplification mechanisms in laminar base flows and structures, coherent structures that are observed in a fully turbulent regime. So what we're aiming for here are reduced order models of coherent structures. So by reduced order model, I guess we mean something that's shy of just solving the full Navier-Stokes equations. I sort of consider that manifestly useful if we can find a way to do that. After I talked at APS, I was sort of accosted at the reception by a person who thought that was just foolishness to try to seek anything beyond, we have the Navier-Stokes equation. Why should we try to do anything else? But if we have reduced order models, we can maybe take shortcuts to understand how we get to predicting and controlling structures and applications. So there are many different approaches for modeling structures, including people in this audience who have worked on different things. Some sort of generic things nowadays is that we need to be aware that our definition of our coherent structures, how we actually define what they are, is really a critical component of their model. If we can't precisely define what it is that's the target of the modeling, then we don't have much hope of deriving equations for it. And the other thing that's interesting to keep in mind now is that we have access to big data and lots of great algorithms for probing that big data, and that should help us with this decades-long quest to model to make reduced order models of structures. So these things are linked, and one nice pair of techniques in the frequency domain that are closely linked are spectral proper orthogonal decomposition for identifying and defining structures, and then resolvent analysis for aiming to predict them. And in terms of big data, what I'll exploit for this talk is mainly data from high fidelity this. That could equally well be data from experiments or other sources. Okay, so the resolvent framework starts, of course, with the full Navier-Stokes equations, does the standard Reynolds decomposition, and for stationary flows, at least, we can also insert the ansatz that we're looking at we're working in the frequency domain. When you put those into the equations and you write things in this kind of abstract operator form, you can arrange the equations so that you have a linear operator acting on the output fluctuations, the Q hat, that's our entire state space of different variables in the flow. It's discretized as it will be when we compute these things. The Q actually also represents each degree of freedom of the discretized system, so the flow variables at every point in space. And then over on the right-hand side, we just put all the other terms that would come from the nonlinear, that are essentially nonlinear terms. So the terms, strictly speaking here, that decay more rapidly than Q hat as Q hat goes to 0. So the idea in resolvent analysis is that we want to think about the fact that this linear portion of the operator, if I invert that and stick it over on the right-hand side, then it tells me that the output Q is related through this linear operator to this nonlinear forcing F. And because we can understand that that linear part of the operator has quite a propensity to amplify certain patterns in the forcing into patterns in the output, the notion is that if we look at if we do an SVD basically of that operator and look at the high gain relationships between specific forcings and specific outputs, that will be a good way to head towards model reduction. So when we put the SVD in here, we get, of course, U sigma V star. So the columns of U are the outputs modes of this decomposition. The columns of V are the input modes, and sigma is this diagonal matrix that represents positive gains between the inputs and the outputs, and which maximizes the rate of evolution. So the kind of questions that are being addressed in the community on the resolvent is does this SVD provide a good basis for the actual structures that you observe? Is it somehow predictive of that structure? And how hard is it to model the right-hand side forcing, and what different consequences of different modeling approaches on the right-hand side? So I'll talk a bit about those. I'm also interested in computation generally, so I also want to stress that this resolvent is not always easy to compute. We would like it to be. We have to discretize the equations of motion using standard or very specialized computational fluid dynamics routines. We have to do that in a way so we can actually perform this singular value decomposition, which places some constraints on what we can do. And as I'll stress a little bit later in the talk, it can be difficult to do this in a way that's free from artifacts. So people here know that from doing global stability and other things that the linear algebra can be part of the toughest part of the calculation. You have to get reliable answers. Okay, so what's kind of interesting is that there's this direct connection between these resolvent modes on one hand and data-driven modes from the spectral proper orthogonal decomposition on the other hand. So we can, well, I should point out that this is what I'll be talking about here was work I did with Aaron Town and Oliver Schmidt. And what we were exploring was the connection between these SPOD modes and the resolvent modes, and also the dynamic mode decomposition. So if we form the cross-spectral density of the response, SQQ, the SPOD is nothing but, this is all in the frequency domain, so SPOD is really nothing but just the eigenvalues and eigenvectors of that SQQ matrix. And of course, this provides a different kind of orthogonal basis than the resolvent. It provides a different orthogonal basis for the response Q. Let me just say a few things about how we can compute these SPOD modes. So one thing I want to say is that it turns out that SPOD is a kind of DMD. So it's we've interpreted as sort of an optimally averaged DMD. And in that process of doing that optimal averaging, it gets some nice robust properties that DMD generally doesn't have. So this SPOD algorithm is not very sensitive to noise because of the averaging that's done. And the algorithm to compute it is classical, right? It's basically Welch's method, the Welch periodogram to compute the cross-spectral density sequence. But what's relevant here is this connection with resolvent operators. So if we just plug that in and do the algebra, we can relate SQQ through this grouping of terms to the cross-spectral density of the forcing SFF. And what you see here is that this provides a very good opportunity for data-driven analysis of this expression, because you see the gain appearing here twice, sigma over here and sigma over here. So we really only need to worry about the high gain forcing modes. If we can find a good model for just these high gain forcing modes, then we'll get a good reduced order model for the response. So that means we have to somehow model this forcing. And there are different techniques that are being pursued around the community on this. I've already mentioned the kind of data-driven approach. There, of course, we can tackle this problem sort of directly based on physics. We can look at the detailed triadic interactions, for example, that are inherent in SFF. And finally, we could perhaps take a different approach and use a more classical kind of turbulence modeling technique. That's one thing I'm going to highlight in this talk. And it's a little bit different from the other things because when we insert a turbulence model into this, we're not just going to modify the forcing, but we're going to actually modify the resultant operator itself with the turbulence model. So we're going to shift terms essentially between the right-hand side and the left-hand side of the model. The other thing to point out here is that there's good reason for hope here because a very crude, obviously too crude model of this forcing would be that, well, it's incoherent, right? It's uncorrelated. So if that's the case, then this SFF is just simply a diagonal matrix. And in that case, you can see that all these things basically collapse. And we have that the resolvent output basis U is the same as the SPOD basis. So we can understand that if somehow this forcing were uncorrelated, then the resultant mode would be the SPOD modes and vice versa. Of course, that's not a good model of turbulence, this white noise, but there are circumstances, and I'll show you some, where in fact we get very good results by just doing something that simple. And that corresponds typically to cases where we have a very strong amplification, you know, kind of to localize disturbances in the flow. So the jets that I'll show you momentarily, little disturbances in the near nozzle shear layer are greatly amplified downstream. And so the detailed forcing of those modes is not so important. It's just we just need a little noise to pick them off. So for certain kinds of structures, this model is actually quite good. Okay, well, with that introduction, I will go through three different topics that are related to this. The first is to try to do a little turbulence modeling with the resolvent, and we did that in the context of turbulent jets. After that, I'll talk about something a little bit different, which is extending the resolvent framework into the nonlinear regime using something called harmonic balance Navier-Stokes approach. And then the third thing I'll talk about is to come back to some of the computational issues with computing the resolvent and try to think about some frameworks for how we can make progress in that area. So this work on optimal eddy viscosity was the PhD thesis of Ethan Pickering, George Regas, Oliver Schmidt, Denny Sipp, Andre Cavalieri, and Petronio Noguera were all closely involved in this work. And so the focus here is on a high Reynolds number turbulent jet, so Reynolds number 1 million. This work really wouldn't have been possible without a really stunningly good large eddy simulation of this jet that was done by our collaborator Guillaume Dress at Cascade using the Charles code that's been developed at Stanford and Cascade. It has a whole suite of really great features that are good for modeling flows like this, and that's kind of a whole nother talk that I won't have time to get into now. But what I can tell you is we have a database of different jets at different Mach numbers, and they have all been carefully validated with companion experiments in Peter Jordan's lab at the University of Poitiers, and all give really a quite nice agreement with what's been measured in this jet. So we feel very confident that this data is at least high enough fidelity to answer the questions that we're using. So this provides us this mass data that we can use to compute SPOD and do other things. And so I'm going to jump in here by showing you over on the right the SPOD spectrum for this flow. So the jet is axisymmetric on average. And so in addition to our frequency decomposition, in this part of the talk, you're going to hear about azimuthal mode numbers M. Those are the azimuthal Fourier transform of the jet. And what I'm showing you on the top plot is the SPOD spectrum for the axisymmetric part. So we'll look at other M's momentarily. And what you see here is kind of a waterfall plot of the different SPOD modes. So the top line is number one, the optimal mode, the next suboptimal modes are below it. And we see this kind of nice gain separation between the first mode and the other modes, at least over a certain portion of the frequency domain. By the way, the frequency here is in Struhal number, and we're restricting our attention for the most part to fairly low Struhal number 0 to 1. The energetic turbulence in the jet can extend up to a Struhal number of 5 or higher, quite a bit higher at this Struhal number. But most of the coherent structures we're interested in the yes frequency regime. So we have this gain separation, but it's not uniformly true. When we look to the low frequencies, which turn out to be very energetic and very important, we don't have that high of a gain separation. And we'll see some reasons for that as we go through here. Down on the bottom, I'm showing you the different azimuthal modes of the jet, just the dominant mode. And you can see that M equals 0 response is not necessarily the dominant response, except that so this like kind of mid-range of frequencies. You have these other azimuthal modes that are dominating the spectrum for the lowest frequencies. I'm sorry, the plots are hard to see at that scale, but we'll zoom in on that here in a moment. Okay, so what I want to do now is take you through some of the observed coherent structures in the jet. And I'm going to do this in a way that where I'm first going to give you like the interpretation that we had in these structures before we got turned on to resolvent analysis. And we just had to sort of guess what they meant. And then I'm going to show you when we apply resolvent analysis to this same jet, how that really brings into focus what the physics of these different modes are. So the first mode here is from the M equals 0 component up here in the mid frequency regime. And I'm showing you some different flow quantities for the corresponding eigenvector. And what we see here is clearly a Kelvin-Helmholtz wave packet in the jet. This was the easy one, right? Because this is something that's been studied for many years in turbulent jets, going back to Gaster and Crichton and others. This is known to be Kelvin-Helmholtz, not just because of the pattern that we see here, but because previous attempts to model this using linear stability theory and parabolized stability equations were quite successful at predicting this. So we know exactly what the physics of this movement. Now we'll take you to the very low frequency M equals 0 mode. And I'll show you what we used to think was a Kelvin-Helmholtz response of the jet at M equals 0. It has some similarities in terms of the patterns, but was never really well predicted with classical linear stability theory. And I'll show you why that was the case as we get to resolving. And now I'm going to go to a higher azimuthal mode, M equals 2 at very low frequency. And here we see a really different kind of response of the jet. And what we actually see here is basically a streak structure. There have been observations of streaks in turbulent jets going back really quite a number of years, but it was really our collaborator here, Andre Cavalieri, and his students. Andre is also here. I know that he had to go pick up his kids, so he's not here at the moment, but this really was Andre that kind of discovered how prevalent this was in the jet. And you can just see it here in the naked velocity field of the jet, where I've now unwrapped the azimuth. And you can see these kind of cascade of streaky structures that are starting at small scale near the nozzle lip and getting larger and larger as we go downstream. So these streaky structures, again, the resolvent will tell us exactly what they are. Okay, so let's get into the resolvent part. So we're going to try to model the forcing, and the approach we're going to take here is to say, well, what if we can have an eddy viscosity model? The eddy viscosity model is going to be very special here, right? It's going to be a mean flow based eddy viscosity that's going to act on the disturbances. So this is not an entirely self-consistent model. It's just an ansatz that we can write down. It's been used by many different groups over the years, kind of loosely motivated by the idea of the triple decomposition. But we're just going to take this and kind of run with it. So we're going to see if we can find a mu T field such that we, with this modified resolvent operator, we can create mu T such that it automatically aligns the first resolvent mode with the first SPOD mode. So we have all our data from the jet, so we can set up this sort of data-driven optimization to say, is there some magic mu T field that would cause those two things to be aligned, right? And if that's the case, of course, then that means that at least in terms of the first mode, a diagonal forcing model would suffice here. And so we've now reduced the modeling of that to a much simpler problem. So the answer turned out to be sort of surprisingly good. So we can find a mu T field such that we can align the SPOD and the resolvent modes. So I'm going to show you a series of plots here that have what we call the y-axis here is what we call the mode alignment metric. So this is just the inner product between the first SPOD mode and the first resolvent mode. If this is unity, then the two spatial patterns are identical. If this is zero, then they're completely uncorrelated. And in between, it's open to interpretation. But what I can tell you is that agreements above about 50% mean that if you look at the plot with your eye, you'll see something that looks similar, right? And as you get from 50% to 100%, that comes into from being like similar to being like exactly the same. And when it's below 50%, you really have to use some creativity to see the difference. Yeah. Good.
So you call it a metric, but would you not want to keep track of the sign? It's a dot product.
Well, the phase of these things, these are complex eigenfunctions, and their phases are irrelevant. So, yeah. So there are two different cases here, what I'm calling the baseline. So this is the resolvent without the eddy viscosity. And there's a footnote here about that calculation that I'm going to come back to a little bit later, but I'll just present that as kind of the baseline case here. So no eddy viscosity model. What we see is that even without any model, this alignment is sort of decent over this range of frequencies where we have this high gain response of the jet. So in the region where the jet is dominated by this Kelvin-Helmholtz instability, even without an eddy viscosity, you get relatively good agreement. It's not really surprising in the end because the Kelvin-Helmholtz mechanism is an inviscid instability. It's kind of insensitive to the Reynolds number in the regime we're looking at. So you get at least decent agreement without any specific value of viscosity. At low frequencies, the unmodified model is useless. The alignments are way down here at 0.1, so these fields are completely uncorrelated. What's interesting is that the optimizer is able to find some UT that brings those alignments all the way up to better than like 80-ish%, right? Which is really quite good, quantitative agreement between the two quantities. So there's a lot that we kind of learned by looking at those optimal eddy viscosity fields, but I think what's a more interesting part of the story is to ask, well, how special is that eddy viscosity field? Does it have any connection with what we recognize as the real eddy viscosity for grams of a jet, for example? So what we decided to do was to simply take an eddy viscosity field from a separately computed grams of the same jet and compare that with the optimal case, right? So this kind of confusing plot here is the result of doing that. So I'm showing you here 3 different azimuthal modes in different colors. If we look in on the baseline case here, right? This is for m equals 0 is the story I just told you. The other azimuthal modes for the baseline case are not very good at all. But you see here, even with this standard eddy viscosity model, and there's a footnote there, right, which is that I calibrated this model. You can calibrate this model. So it doesn't take the full eddy viscosity field out of the grams. It takes the full eddy viscosity field times a constant. Like the full eddy viscosity field would be the eddy viscosity for the mean flow, right? We're looking at an eddy viscosity for the disturbances. So it sort of stands to reason that it would be less than the full eddy viscosity field. So we allow ourselves one constant here to tune that eddy viscosity field up and down. And the magic number here that turns out to be optimal is 0.2. And so this is another optimal calculation of the structure of the eddy viscosity field fixed from the RANS. And again, you see that this really does substantially improve the alignment. It's almost as good as the optimal mode in, especially for the m equals 0 mode. It brings the alignments up to at least like sort of 50% over most of the frequencies, so that at least it's sort of qualitative agreement, if not quantitative agreement. So that's nice, right? Because that says that we can take this resolving calculation now and sort of trust that the answers that are giving us auto-model the structures that we observe in the jet. So this then gives us an opportunity to learn more about these three different instabilities that I showed you earlier. So the Kelvin-Helmholtz mode is the least interesting one. Here I'm showing you sort of a carpet map of the energy levels and the gain levels in the corresponding SPOD and resolvent spectrum. You can see already from the carpet plot here that there's a qualitative match between the gain and the actual energy level of the structures in the flow. Zooming into this region of the Kelvin-Helmholtz, so n equals 0 at mid frequencies, we see that the baseline alignment was already pretty good, but the optimal or the standard eddy viscosity model, which is what's plotted here, brings that all the way up to like 94% agreement. So what you want to look at is the left column, that's the data from the LES, and the middle column here, that's the optimal RAMS eddy viscosity. So really stunning agreement. Now we go down to the m equals 0 mode. This is the funny one that I said we used to think was a Kelvin-Helmholtz response of the jet. It turns out it's not. It turns out that when you look at the resolvent, you have access to both the forcing of this mode and the response. And what we discovered is that this is, well, it's what we're calling an OR. It's a classic OR mechanism that's at play in the jet. It takes structures that align against the shear and rotates them downstream to structures that are aligned with the shear. The forcing of this mode is associated with particularly near the critical layer of the jet. It has all the hallmarks of kind of the OR with the bonds of the jet. And it turns out, yeah.
Can I ask a quick, so when you do this matching with the resolvent, you're actually also matching the forcing too, is that right? Or is that not correct?
Well, no, so the forcing becomes almost irrelevant, right? It becomes a single constant because we're aligning the two modes, and so they're related by a single constant. And the constant here is not, these are linear predictions, so we're not matching just the structure.
So it's just the eddy viscosity that you
The eddy viscosity causes the structure to match.
And then how do you make the deductions and all mechanisms?
Well, by looking at several different things, right? So looking at the patterns that you see in the different variables. So comparing like, the velocity components to the pressure. And
don't you see that in the SPOD mode? It's the same mode.
You do, it's the same. I mean, so now what we see here, right, is that by getting this good alignment, right, now I can take a resolvent and I can understand better what actually produced this mode, because the resolving gives me not just the output, it gives me the thing that forced that mode. So the big difference here between the Kelvin-Helmholtz and the OR is that if I'm not showing you the forcing here. If I showed you the forcing for a Kelvin-Helmholtz, you'd see a very localized region of disturbance near the nozzle lip that is amplified downstream. When you look at the forcing for this OR mode, it's very different. It's a spatially extensive forcing along the critical layer of the jet. So it's like you could think about it as just random turbulence that's exciting this kind of critical layer OR type mechanism.
There's no structure in the forcing, that's what I'm getting confused about. So I don't understand what extra you get by doing the resolvent flow analysis.
There is structure in the forcing, right? So the forcing nodes and the response nodes for the resolvent are, the forcing nodes is the structure, not the amplitude, but the structure of that force that then produces a given output. I wish I had a plot here to show you, clarify.
But I thought you just said the forcing was generic and you don't fit it to anything. It's the resolvent, the viscosity in the resolvent that you adjust to get the right response that matches what you see in the SPOD.
Well, when we tune this eddy viscosity model, right, we still have a resolvent calculation with the eddy viscosity resolvent, right? So we still get a set of forcing modes and we still get a set of output modes. And we still get gains.
What do you call them? The forcing modes, the ones that
The columns of B, right?
Oh, okay. Thank you.
It's the optimal basis, an optimally amplified basis to describe a generic force.
Sorry.
No, sorry, I'm sorry. I didn't get
Stop. So first, I guess I should have probably been interrupted all along, but I'll keep it brief. Just these are zero frequency modes. Is that right, or just nearly zero?
Well, the one I'm showing you here is nearly
Oh, I see.
zero
It's
frequency.
exactly zero.
It's not exactly zero. So we can compute resolvent modes at near zero frequency or at zero frequency exactly. I can't do SPOD at anything close to actually zero because I think we need an infinite amount of
Okay,
data.
now that's kind of, can I just go back one? Could you just go back to the algebra real fast and then maybe I'll take it?
Go back to what?
The algebra.
Oh,
Let's
sure.
come back with that version.
Which one?
Yeah, the one just after that, yeah.
So I think it's you're decomposing something into U and V.
I
The two fields.
think the one you want is this one.
Yeah, that's the advantage of this approach, right? You're getting U and the V fields
Yeah.
from one field in the SPOD. Is that what the decompositions do?
No, the decomposition is taking the linear operator, right? So the linearized Navier six.
Yeah.
The resolvent modes are the decomposition of the operator. Right? In the case of CFD, that's a matrix, right? But in general, that would be an operator, and this is the SPD of that operator.
Yeah.
So it's a linear operator, and so the SPD gives you a relationship between forcing on the right-hand side and the response.
But that's the advantage of doing this mapping macro flow mode. You're taking an SPPOD mode and decomposing it into a U field and a V field.
No, the SPOD modes are another basis for just the U's, right? It's a different basis. And in general, they are different, right? It's the eddy viscosity model here that we've kind of pushed on this to draw them closer to being the same thing, right? So if they're the same thing, then the same forcing from the resolvent would be the thing that gave you the response.
I'm going to talk to you at the end.
Okay. Sorry, I didn't make that clear. Mike, did you have another question about the algorithm?
Go on.
Or the question in the chat, is it?
Okay.
Is it?
Yes, can I speak?
Yes, go ahead.
Sorry, Tim. I just want to have a quick comment. Actually, the eddy viscosity is something that, I mean, of course, come from the Reynolds and Hussein back in 1972. Not the, and in the, I think the Carlo and I used it in, and even Javier used it actually 2006. I think it's something that I should tell you.
Well, I'm quite aware of that, Young. Thank you. I'm quite aware. I'm sorry I didn't give a kind of history of that. What I told you is that it's been used by others, and I mentioned the triple decomposition, which is the Reynolds and Hussein.
Yeah. Anyway,
so thanks. Yeah.
Cool.
All right. All right, there we go. Okay, so this can be identified as OR mechanism was the point there. And then finally, if we look in on this streaky structure, again, the resolvent is very helpful because it again gives us both inputs and outputs. And what we can see here is kind of the classic imprint of the lift up mechanism, right? It's been well studied in well-bounded flows. So these streaks are produced by the same kind of lift up mechanism that we have in turbulent boundary layers. The agreement here, and this probably gets to Dwight's question about zero frequency. The agreement here isn't nearly as good. There's two factors here. First of all, the eddy viscosity film wasn't able to just exactly align these two structures. But moreover, the SPOD at these very low frequencies is really hard to converge. So when you look at these pictures, you should hold them as a statistical convergence issue that they're not perfect. We just don't have enough data to get a perfect version of those structures. Okay. Great. So these streaks, what I'm showing you on this picture is this global streak. So this is the global SPOD spectrum, the global resolvent calculation. And it's showing you this very huge streak that's all the way down the jet column. And this is an n=2 version of that streak. But as I showed you before, when we look at the actual velocity field, we can see this whole sort of spectrum of streaks, right? Starting from small scale upstream to large scale downstream. And so we can take the same framework of SPOD and resolvent, and we can limit the domain to smaller regions near the nozzle exit. And by doing that, you can reduce all these same structures, those in the SPMD, and then resolve it to show you kind of this hierarchy of these different streets at different azimuthal modes and so on. So these don't show up in the global spectrum because they're not energetically important over the whole region. Okay, we'll summarize this first part. So the resolvent structures with the eddy viscosity model give us, at a minimum, qualitative agreement, and in many cases, quantitative agreement of this observed SPMD structures over the entire jet spectrum, at least Screwball 1. It helped us identify what the mechanisms behind these observed structures are. And in particular, it allows this kind of further understanding of how lift-up mechanisms can take place in jets in the same manner that occurs in boundary layers. Just to mention a kind of future direction here, I think this gives some hope that RANS-based approaches to predicting structures via this kind of resolvent, this one eddy viscosity model is probably not going to be good enough for all of that, but it shows that this is at least a promising avenue of thinking. Okay, so the next part, and I'm going to go very briefly on this part to economize on time, and because this work is going to be presented, I think, by George next week in the workshop. So this was work with George Regas and Yenny Sip, and we were interested in sort of extending the resolvent framework into the nonlinear regime via this kind of harmonic balance approach. So in particular, what we wanted to look at is if we look at this kind of minimal seed problem, but not in the time domain where it's very typically been looked at, but in the frequency domain. And we use the resolvent analysis. And now, again, about a laminar base flow, can we use that to look for these kinds of generic forcing of the flow, or not generic, I get in trouble with Rich, I didn't mean to say generic. This kind of forcing in the flow that would lead to the fastest transition state. So the framework here is to include the nonlinear terms now explicitly. So we have our nonlinear term acting on Q hat, and then we have a small but a non-zero forcing field that's added here. And the idea is to keep that overall forcing amplitude, the norm of that thing, fixed at some number, and then find the structure of that F that gives, through this nonlinear relationship, the fastest transition. And so that's done using a kind of Lagrangian optimization technique. So we define a cost function. So this is going to be the thing that tells us how big the nonlinear disturbances are growing. And what we chose to use here was the integrated wall shear stress, the difference from the laminar value. So this is going to give us that forcing field that gives rise to the quickest departure of the shear stress from laminar value. And then we constrain it to satisfy these harmonic balance equations. And then this other constraint is to hold the overall forcing amplitude to some fixed constant that we're then going to adjust. So I'm not going to go into the details here again because, as I said, George is going to talk about this work next week. So I'm going to skip a bunch of stuff here and just sort of show one kind of tantalizing result that you can get with this model. And there's some background here and caveats that won't come through with this simplified view. But if we if we kind of vary that forcing level, and we vary the sort of number of modes that we retain, we can actually see different kinds of simple transition scenarios occurring. And in this particular one, you have an initial excitation of oblique waves, which then through nonlinearity leads to a streaky response. And then a further breakdown of the streaks in these kind of lambda type vortex structures. And for this very low dimensional model here, so we have just 3 frequencies and 2 span-wise modes in the flow, we're able to not just get these structures, but you can see from the output of the calculation in terms of the mean, and not mean, but in terms of the, well, yeah, in terms of the mean zero frequency velocity field, you can see that starting as we kind of march downstream in X, starting from this initially laminar case, we get this kind of, you might think of as a nascent log region here on the plot. So it's not, this is just past, sort of transition here, but that seems promising in terms of sort of reduced order modeling. Again, there's a lot more that we can learn from this that I skipped over, but I just wanted to kind of highlight that result. So let me just close with a few remarks about computational issues. So starting at the end there, where we had the harmonic balanced Navier-Stokes equations, we can write those equations down in the frequency domain. We can write Navier-Stokes down in the frequency domain as we have here. And we can do these harmonic balance calculations like I just showed you with a few frequencies. And those are useful calculations. They kind of give us frequency space equivalents of both kind of self-consistent models, as well as structures and solutions that are remnant, that are really the same as the exact coherent structures or edge states, right? We're just finding them in the frequency domain rather than the time domain. So that's one really nice use of these harmonic balanced Navier-Stokes equations. But the difficulty is that there isn't necessarily a stable solution with a fixed truncation of frequency modes in the flow. So if we postulate that there is, right, and then compute that, we're also going to be able to see what the truncation error is, right? It's going to be non-zero. We're not exactly balancing the Navier-Stokes equations. The only way you could then resolve that truncation error would be to add more and more frequencies to your basis, right? The standard sort of thing you would do with simulating any nonlinear solution to Navier-Stokes. But the problem is here that if you just simply add more and more modes, what you'd be aiming for without further modeling or ideas is simply a frequency space solution of like a direct numerical simulation, which is likely to not be an attractive, it might have a few attractive features, but by and large, that's likely to be much less efficient than the time marching methods that we're all familiar with using for Navier-Stokes. The only sort of bright spot you could imagine to that is you could have a time parallel calculation, right? You wouldn't need to do a sequential solution of Navier-Stokes. You just put the whole thing in the frequency and then you can do it all as one big system at the same time. I don't know. It's an interesting thing that I'm hoping to explore more, but I'm doubtful that this would be like an efficient way to approach Navier-Stokes is the point.
Well, I believe Fred Wright's photographer is going to speak next week, and he's going to advocate for that.
I'm sorry, I didn't hear your
I
name.
think, well, Fred Wright is going to speak next week.
Okay.
And, he may be advocating for something.
Okay. Well, I'd love to learn more. I mean, the point that I'm wanting to make here is that there are probably happy in-betweens here, and there are probably very interesting and useful turbulence modeling approaches in this frequency domain. The kind of hope is that with this simple transition scenario I showed, we could get with just a few modes, right? I mean, if you if you can do twice that many modes, you can get that much richer structures and so on. So my interest here wouldn't necessarily be in kind of a paradigm shift away from time domain calculations, but more on the modeling side. Still, there are issues with that have to be confronted. So in the last part of the talk, I'm going to be showing work that actually started again with Aaron Town, but it's certainly been being done by my student on the end there, Omar Kamal, and then some George and Ethan are also participating in this, and that's Matthew Lakeland from Bowie, who also been collaborating with this. So broadly speaking, the first computational challenge is you need a linearized and adjoint linearized Navier-Stokes to do any of this. And it takes a graduate student about 6 months or so to take a code that's not that way already, take a nonlinear code and find a good self-consistent linearization and adjoint linearization of the code. Automatic differentiation is being used in some camps for doing this. our experience with that is that it's still not ready for prime time, despite all of the kind of modern machine learning approaches.
May I ask?
Oh,
Yes.
If it's to be just Navier-Stokes, why do you need automatic differentiation, and why should it be difficult since Navier-Stokes is merely quadratic?
Well, so it's not just it's just so is that Lorette?
Yes.
Hi, Lorette.
Hi.
It's essentially the whole CFD algorithm that we're linearizing, right? Not just the continuous governing equations. Does that make sense?
No, but perhaps I'll ask you later.
It's a code. It's not the equations. It's the code that we're linearizing.
Yeah, but doesn't the nonlinear part of the code follow the fact that you have a nonlinear term in the equation? Isn't the linear part of the equation simulated in a linear way by the code and so on, but apparently not?
Well, if all you need is the forward linearization, right, you can get that from the nonlinear code by, in an approximate way by just differentiating directly, right? But
Right?
but we need the adjoint of that as well. And so, depending on the form that you get the forward linearization, if you get it as a big sparse matrix, then the adjoint is just the transpose of that matrix and so on. But that's not the typical way that the linearization of code works, right? So I'm sorry if I've confused.
No, just go ahead. Just go ahead.
I just want to also point out that this part doesn't really have much to do with the nonlinear term, right? This is you are linearizing the whole thing, including the nonlinear term, right? But to do these calculations for resolving, you're just getting the linear nonlinear.
Sure.
Okay, thanks. I'd be happy to talk offline more.
Sure.
Another thing I want to highlight here is that whenever you're doing numerical linear algebra, you have to worry about conditioning. And with resolving calculations, one of the things that really can be very problematic are the boundary conditions that you have on your compressible, in our case, Navier-Stokes equations. You have things like non-reflecting boundary conditions, inflow, outflow conditions, and so on. And we know from boundary condition work going back decades that there are lots of different spurious modes that can be excited by imprecise or not good boundary condition treatments. And we also know that those things can interact in a very substantial way with the numerical discretization itself. So, to be completely transparent, a lot of the calculations I showed you are not easy. They need a human in the loop to make sure that the thing that's coming out of the resolving calculation is not just some spurious numerical artifact. I'm just showing you some examples here of like horrible, slightly better and correct solutions. And you could ask how I know that they're correct, and I can tell you what we look for. But the point is, it's really easy to get artifacts here. So this is something I'm just mentioning because it just doesn't appear in the literature, and a lot of people are computing these things, and it's good to be skeptical of the results that you get. One thing that I've highlighted at the bottom here is that if you say that you want to do this resolving calculation, at least for this kind of two-dimensional base flow that we have here, and you want to go to high Reynolds number, it becomes computationally intractable because the resolvent structures are as fine at high Reynolds number as the turbulent flow would be on a grid. So you need grids that are probably even finer than a DNS grid to get good resolvent calculations for those. It's certainly possible to do this for flows that Beverly has considered with channel flows with one homogeneous direction. This is not so much of a problem because we can use lots of grid points in one direction. You can get really good, sort of asymptotically high Reynolds number results there. That's difficult to do for these flows. And this eddy viscosity model, in a sense, you could think of that as a regularization of that problem, right? If you just go in and compute those results that I showed you without any model, you really have a problem at the high Reynolds number. And that's the caveat I wanted to say about the original comparisons. Everything I was calling the baseline resolving calculation before was actually with a Reynolds number that wasn't 10 to the 6. It didn't match the actual calculation. It took the range of 30,000, which was the highest we could actually compute these things with. So that's a big issue. The computational expense. I can kind of skip over this. I think there, you know, the people that are the numerics types who are interested in talking about this, I'll be here all week and we can have discussions about this. There are some trade-offs for how you do this algorithm. You can do it within the time domain. You can do it in the frequency domain. The direct solvers are really good if you have a nice sparse linearization. The multi-frontal algorithms are quite competitive. They bring down the cost of doing the LU of the system to you know, powers of 1.6 or up to like maybe 2 times the number of degrees of freedom. So that makes it plausible, at least, to do 2-dimensional base flows with this. But as you push up the grid, that still that still pushes the boundaries of what you can compute. And the reason isn't because of the CPU, it's because of the associated memory requirement for these direct solvers. So you run out of memory long before you get bored of waiting for the results. One thing I'll just highlight here is a technique that we've been working on for a number of years now on a parabolization of the linearized compressible Navier-Stokes equations that is similar in spirit to what's called parabolized stability equations, but is based on a more rigorous approach. I should say more rigorous, it's either rigorous or not, right? It's based on a rigorous approach to parabolizing the equations. And with this one-way Navier-Stokes, you can reduce these exponents because you can march the problem in a streamwise direction instead of computing one big global solution. So just to sort of show you that you can at least get the same results with that, we can do optimization in the same way. So you can essentially do the SVD via ohms. Here I'm showing a high-speed boundary layer. This specific case was taken from the study of Muguet et al. And we've done this kind of global optimal input-output analysis for this boundary layer. And I'm just showing you that for both the forcing and the response to ohms equations can give you a really good approximation of that system.
We've got a question. Like, are you just about to finish?
Yeah, I am. Yep.
All right, well, go ahead.
In fact, I am finished. Right?
Tim, may I ask you a question for the last slide, the one before?
Yeah.
I really actually like this comparison, which is remarkably good. But the one thing I spot is the Mach number is 4.5.
Yeah.
So I just wonder, you get the same amount of the agreement when you lower Mach number, for example, say Mach number 0.1.
Yeah, for a boundary layer you do. We've done this over the entire regime from essentially incompressible all the way up to sonic. And for a boundary layer, ohms is really good because the parabolization there are many modes that are where upstream acoustic influence is kind of important, right? So,
Yes.
so your question reminds me to make a caveat about ohms, right? When we talk about parabolization, right, you would have the same problem that you would have for any kind of parabolization, like the boundary layer equations, for example, when you have any reverse flow. So this is not necessarily an appropriate technique for separated flows and so on. So it's really for boundary layers and jets and other kinds of layers.
Okay. Yeah. Thank you.
Okay, questions from the room, please.
Can I just a philosophical question?
Yeah.
You started by saying that coherent structures are important. You are assuming that. And then you said that things depend on how you define the coherent structure, which I agree with. But then you speak about that. I mean, you seem to say that for you, coherent structures now are the singular vectors of the LVD. Is that what you're saying?
No, I'm saying that coherent structures are the eigenvectors of the SPOD, are the SPOD modes. That's what I'm taking to be the definition of the structure. So those are optimally coherent modes from space-time modes from the
They're optimally, they represent optimally
second order statistics.
Are they coherent in any sense?
Yeah, I mean, well, that, you know, if you wanted to see what their instantaneous imprint is, you can look for them in flow, and Oliver Schmidt has been doing that, for example. I mean, you can, you know, these structures exist both instantaneously in the flow and they exist in the out. This is an average of the structures I'm showing you. So, you know, it's a different question to ask of you know, whether you can see the signature of those structures instantaneously in the flow. Right? These are the statistics of them. The statistics of them are.
But why are they coherent? In which sense? Because then at the end you mention also the coherent structures are why.
They're coherent because they're coherent because they're coming from the correlations. Right? I mean, it's eigenvectors of correlation. That's what I take to be almost a definition. That's what I take to almost be the definition. Sorry?
That means that they are a good basis for the instantaneous field. That doesn't mean that they are coherent. I mean, in which sense? I mean, what do you call a coherent structure? What are you trying to model?
It's the thing that captures the most variance in the field. That's what I would take to be a standard definition.
So why do you call them coherent? I mean, coherent, I always thought that had to do with time.
I understand that word is used in different ways by different people, right? So this is how I like to think about them, right? I like to take this statistical.
Why then are they related to models or you know all the other without coherent structure? So fixed point of people compute.
Well,
H states. You also mentioned H states.
Well, if you're asking about that comment specifically, it's a different answer than the generic philosophical comment, right? So that was that part where I made a comment about the edge things. Those were nonlinear calculations. With full mappers, so with truncated non-Stokes equations. So those are the same thing as edge states and so. Right? But I think your philosophical question is why is SPOD a good way to define coherent structure? Is that what you're asking?
And essentially because you said, and I agree that what you get depends on your definition. What would be the effect of defining it in other ways? That for me, it has something to do with time.
Well, yeah, I understand. Yeah, I understand that. I'm not gonna. I wouldn't try to make a case that I'm not trying to make a case that this is the only way one can or should approach this. I'm like.
Can I ask? I mean, related to that, essentially, I think Javier's point is that coherent structures need to persist in space and time over an appreciable time span or length span.
Yeah.
So, and you could certainly.
Well,
but calculate that, right? At different time steps to see.
No. I don't need to, right? These manifests would do what you just said, right? These are space-time modes from the full space-time correlation, right? I'm doing it in the frequency domain, but that's kind of irrelevant, right? These are the space-time coherent structures out of the full 2-point.
Yeah, so they do survive over a long time.
By definition, they survive over a long time.
I mean, they're more monochromatic and they are wave in time.
They're not well, they're one frequency at a time, because that's the optimal way to do it for stationary.
Yes, but that's why we fix things. I mean, you're saying that these are more chromatic things. They have a frequency.
Yeah.
Your argument is wave packet based, right? But you were thinking about it as wave packet that was just a combination of these.
Well, I think nothing more non-linear. I get what it's completely non-linear. This work has nothing to do with it.
Well, there's two aspects. One is if you want to track something that you follow by eye, that is a combination of these modes, right? These things moving relative to each other.
Not all by eye, all by equation.
All the things that you track in your channel would be modeled as a combination of modes.
Yeah,
Yes. But then the other questions about it.
I'm not terribly proud of the things I tell in my class. These are obviously artificial things that have to do with my eye.
Yeah.
Fit and cube.
Because the definition of coherence, right? You see it.
Yeah, but I'm trying to find some definition that doesn't depend on my eye.
Well, there you go.
No, that's a basic. You're finding a good
It's
basic.
not just the basis. I mean, it's not just the basis, right? It's
What
not
is
an arbitrary basis without, it's the optimal basis for computing statistics.
Okay, so it's an optimal basis for computing statistics. It doesn't.
The
pass
sta-
dynamic.
the statistic we're talking about here is,
What is
the statistic we're talking about here is the coherence.
Yes, I mean, what is the dynamic? The dynamics is the thing
The
that.
dynamics is here because it's space-time modes. The dynamics are here.
No, that.
Yes, they are. They're here.
Kinematics is, I mean, it's kinematics in a different.
No, it's not kinematics. These are frequencies, these are space-time modes. They're not your old space-only POV modes.
Could we maybe just call them periodic orbits because isn't that what they are?
No,
They could be. So in the case of the harmonic balance simulations, that's exactly what they are, right?
Yeah.
But in the case of doing SPOD just on data, you can't, I don't think I'd want to interpret them that way, right? These are structures that optimally optimally capture the coherence.
Frequency there.
Can I just ask, just an algorithmic point here? So when you process the data, you do a Fourier transform in time,
Yes.
and then you take the fluctuations and then find the correlation in those. The 2-point
Yes.
correlations, and then if the leading eigenvalue of that,
Yeah.
you're calling a coherent structure.
Yeah, that's exactly right.
Yeah.
I mean, you don't just, I have to say, you don't just compute the Fourier transform.
You do something clever, I guess, but that's
You
it.
gotta do average, right? You gotta
Yeah.
use.
You're taking a fluctuation with one given frequency and doing a
And how it's
correlation.
correlated with every other. You do everything in the frequency domain, so it's cross spectral density, but in the time domain, this would be the correlation.
I mean, my question actually, okay, I mean, you can call coherent structure to anything that you like.
Yeah.
But then you said that's consequences.
Yeah.
What are the consequences of your data? What have you thrown out?
I'm not sure I'm not sure how to answer that, Javier. I guess, I'm not trying to be dogmatic about this. Like, I'm just saying that this one way to describe what you mean by coherent structures would be to describe them as the principal components of the correlation matrix. Right? That's one way to think about defining it. It has merit in this case because they're not just patterns in the flow. These are space-time correlated structures that are having the biggest imprint on the second order statistics. So I can't be more precise than that. And I'm a bit jet lagged, so if my terminology isn't coming out just right, I apologize. But I can't justify it any more than the statement I'm using.
Question from the chat. Idris, would you like to go?
Yes, thank you for the lecture. Sorry, I was confused. I thought that the lecture is supposed to be in R2 in the Center of Mathematical Science, so that's why I'm online. I'd like to ask a question which is a little bit simpler than the points being proposed here. Now, once you have found these, regardless what you want to call them, bases, coherent structures, how are you going to get a reduced model? Which equations are you going to project on them? Is it the Navier-Stokes or is it which equation? How are you going to use them effectively other than, like to produce dynamics, to produce something? Can you just elaborate on that? Because I have second part based on that answer.
Sure, yeah. I think there are probably multiple different paths you could take, but the resolvent modes are already essentially solving the linearized equations, right? So if you insert a forcing model into that framework, you directly get predictions, right? So it's already kind of comes equipped with predictive framework. You pose model, we calculate response.
So you project like linearized Navier-Stokes or Navier-Stokes? Is that what you say?
Correct.
Yeah. Then
Yes.
I have second question. Now I'm a mathematician. I would like to be a little bit more, I wouldn't say completely rigorous, but semi-rigorous. Now I have an equation which is like the Navier-Stokes equations. You take the most energetic modes, so if they are optimal in some energy norm, but then the equations involving gradient, involving Laplacian, and if you are optimal in the L2 norm, you need not to be optimal in the gradient norm or in the Laplacian norm. So why should I think about the truncation or ignoring the Laplacian of the higher coherent modes or coherent structure modes is small? I mean, we have like physical argument for that because mathematically I cannot see it. I mean,
no, I don't. I think no, I don't have an answer for that. I mean, I think at the end of the day, and I didn't, there's a few details I skipped over, but so our whole framework here is based on, doing this for the discretized equations. So like all the hard CFD that goes into that discretization and making sure that it's kind of good, right? I skipped over that part, right? But that's important, right? And so after they're all discretized, right, then all of this is kind of easier. It's linear algebra. But your point still comes back, which is that I chose a specific norm to optimize for my resolving, and that's completely arbitrary, right? That's up to you to define whatever metric you want, right? In the nonlinear part, we were using the shear stress metric, which is a little bit different, but everything else I showed you is optimized with a compressible energy norm globally over the entire domain. And you get different views and different structures if you look at different subsets of the domain and different. If you looked at a gradient norm, as you're suggesting, you would get different views. I think I'd say that's a plus rather than a minus, right? Because it allows you to vary that norm and see how it affects the bases that you get for the result. You can always compare those data that you have.
Yeah, I partially agree. Thank you for the answer. I partially agree, but I not completely agree. And let me tell you why. Norms are not equivalent when you are in infinite dimensional spaces. And therefore, it's not like basically we have arbitrary norms. We have to choose the right norm that preserves the dynamics. And therefore, we need to go for higher order norms to make sure that the vector fields are close in order if you like to do something about it. But anyway, thank you very much for the answer. We can talk more maybe in person next week, but this is the point I wanted to clarify. Thank you very much.
Thanks, I appreciate the point, and I'd love to talk. I agree with what you just said, by the way. I do agree with you.
Okay, any further questions? All right, let's call it quits. Thanks very much.
You.